Everyone, and welcome to the Homework 9 walkthrough. So in this homework assignment, we are going to be covering a lot of greedy algorithms. This assignment is meant to be a little shorter than the others, so I went ahead and released this walkthrough today just to make sure that you guys had an opportunity this weekend to, take a stab at the homework and see how much progress you were able to make. Again, one of the things with greedy algorithms is that they usually do work. They usually work, or usually not hard to come up with. Not hard to come up with. But it can be hard to understand why they work, or like to convince yourself that they actually work. So in this homework, I think a lot of you are going to have a good opportunity to actually make really good progress on your own. So I figured I'd give you guys as much time as possible to do that. But again, we always release walkthroughs just in case you're getting stuck and you don't have a chance to come to student hours, and especially since Friday and Monday were both school holidays. So most of you are probably, working on your own or doing something else. So anyway, let's get started. Let's take a look at problem 1. So this is problem 1 here. Let's zoom in a little bit, make sure that everybody can see that. And we start with the problems talking about greedy strategies. So here we start, with the problem statement. So we're going to have G, which is a graph, right? So this is, by graph, we mean it's a set of vertices and a set of edges, which is an undirected, unweighed graph. So there's no edge weights, there's no direction. That means they're connected, and the edges are undirected, which means they connect both vertices, both from U to V and from V to U. Okay, we say that a vertex V can see an edge if V is an endpoint of that edge, right? So what does that look like? Let's actually try to draw out a couple of graphs here and see if we can do some sort of drawing so I can show you. Right, so we're gonna have a couple of let's set down a couple of vertices. Yeah, just real quick. Okay, so let's say these are our vertices. We've got a couple of them, etc. And what we're trying to do is we're trying to find a set of vertices. Let's draw some undirected edges between them. So let's say, this is connected to this, and it's connected to this one, and maybe this one's connected to this one, and this is connected to this one, and this one's connected to this one, or something like that. So we can we talk about, so this is let's say this is my graph, and then what we have here is we're defining that V can see an edge if V is an endpoint of that edge, right? So in this case, for example, this node here can see this edge, this edge, this edge, and this edge, right? So basically all the edges it's connected to, it can see. And then what we're asking here, say we have a set S, that's a subset of V, right? So we have a smaller set of nodes. So we're going to consider a smaller number of nodes. So let's say, maybe we consider, this node, and maybe this node, or something like that. Maybe we consider those two nodes, and we say that that set is all seen if every edge in E is seen by at least one vertex of the ones we picked. So we can see that actually these two nodes here are all seen, because this node sees, it sees this edge. It also sees this edge. It also sees this edge, and it also sees this edge. So this one node sees all 4 of these edges, and then this node here sees this last edge because it's connected to it. And now, just with these 2 nodes, right, just these 2, we actually see all of the edges in the graph. So these 2 nodes, this S, so we said, if this was node 1 and this is node 2, then we would say, with S, 1, 2, just those 2 nodes, that set is all seeing. In our example, okay? So that's just understanding a couple of definitions. Now we consider the following greedy algorithm. So we say, S, our set starts empty, and then while G has edges, what we're gonna do is we're gonna pick some edge. Okay, so we don't specify, this is actually interesting, we don't specify how we pick the edge. Okay, so in your head, you can think, pick at random, right? That's what the algorithm is saying. Like, just pick some edge. I don't actually care what edge you pick, just pick some edge, because I'm gonna do this greedily. And what it means by greedily is gonna say, well, I'm just gonna pick some edge, and then I'm gonna add those two vertices to S, right? So whichever edge I pick, I'm gonna add the two vertices, because that's how that edge, I can guarantee that that edge is all seen. And then what I'm going to do is each of those vertices, right, I'm going to remove all of the adjacent edges from G. So, in this case, let's go back to our original graph. What that might look like is, we pick some edge. So let's say, we pick this edge, for example. So we're going to pick that edge. And then what we're going to do is we're going to add the two vertices that edge hits. I'm recording. You need me?
Okay, guess not.
Okay. I'm gonna add those two vertices to S. So that's this step in the algorithm, which is S add U, S add B. Then I'm gonna remove U and all its adjacent edges from G. So that means I'm gonna remove this edge. I'm gonna remove this edge. I'm going to remove this edge. I'm going to remove this edge. Then I'm going to remove this edge. What am I doing? I'm basically removing all the edges that these vertices can see. And then, in this case, we're done. At that point, we actually pick these two vertices, and now G has no edges, so we're done and we return S. So you can see that this actually returned 2. So that's how the algorithm works. So we're going to consider that algorithm, okay? And then the first question for 1.1 is proof that find all C in subset always returns an all C in subset. So what this means is we're expecting a short but complete argument as to why the algorithm always returns an all C in subset. So basically you want to show like no matter what S is returned, S is always all seeing. And this should be pretty easy for you guys to see. I'll encourage you to pause the video and think for a second, like, why is it that this algorithm will always return a subset of vertices that sees all the edges? Cool. So one way to see this, which is very, kind of direct, is just consider, let's assume the opposite. Let's suppose S is returned, but does not see all the edges, right? So if we return an S that does not see all the edges, that means that there is some vertex, there is some edge that is not seen, right? So there is some edge that is not seen because we're assuming that whatever S we return in this algorithm, we're assuming it is not all seen. So there's some edge that is not seen. Now, if an edge can only be not seen if at least one of the vertices, actually both vertices are not in S. So that means that, there's some edge that's not seen. Let's call it edge UV. Then this means that U is not in S and V is not in S. So both U and V are not in S, right? Because if they were in S, then this edge would be seen. And we're assuming that we did not return an all seen set. Therefore, there is an edge that is not seen, which means U is not in S and V is not in S, right? However, if we look at our algorithm, this edge would have never been removed from G. Why? Because we only remove edges that have U or V that are adjacent to U or V. So if, and then, U and V are added to S. So if both of the endpoints were never in S, then that means we never removed this edge from G. But then the algorithm, the while loop, but, therefore G still contains edges, but this is a contradiction because we assumed that we had returned this set S, right? But we cannot return until the while loop finishes executing. So this is one way to argue that our algorithm always returns an all seen set. This is called like proof by contradiction. Okay. Another way that you can argue this is you can just try to do like a more straightforward proof, right? So you can say that if there's an edge in G, then we add, both endpoints to S. Therefore, that edge is seen, right? We also add all other edges seen by UV, right? So whatever edge we picked, we add not only the edge that we picked, but we add all other edges that are seen by UV, right? And we don't stop until there are no unseen edges. Therefore, we return an all seen set, right? So that's basically why this algorithm works. It always returns an all seen subset. But now what you want to consider as well is you want to consider 1.2, which is give an example of a graph where find all seen subset does not return the smallest all seen subset, right? So this is actually a greedy algorithm that's wrong because it does not return the smallest all seen subset, okay? And all we're looking for here is an example graph and a brief justification why it does not return the smallest all seen subset. And honestly, we might even, again, I don't tell you how to pick the edges, right? Like, how are the edges picked, right? So you can assume the algorithm, for some ordering of edges will return the wrong answer. And honestly, like even this graph that we just randomly came up with, I think you guys can probably see pretty clearly a set of edges where, we might pick the wrong nodes. So what I'm going to do is maybe I'm going to add an edge from here to here, for example. I'm going to add, an edge from here to here. Actually, I want this to be curved. Let's do a curved connector. I'm going to add an edge from here to here. Okay. And what we're going to see is that, actually, let's think like the most extreme example is probably the easiest. So a very, very, right. So we need to find a set of edges that we pick where we end up with an all seen set that is smaller. Now, obviously, you guys should be able to see that this node let's connect these two. So this node and this node let's connect these two maybe. Okay, so this node and this node are the minimum. So with these two nodes, we see all the edges, right? There is no edge that does not contain these two nodes. Now, the problem is that our algorithm, right, does not know this ahead of time. So you could imagine that instead, let's undo the coloring. Okay, let me go back and add this edge. You could imagine it picking 3 nodes, right? Because what does it do? Let's say it picks this edge first for whatever reason, right? Again, we don't tell it which edge to pick. You can pick edges in any order. So it picks this edge first, which means it's going to add this node, which is good, and it's going to add this node. So that alone, it is already adding 2 nodes that are not sufficient. And actually, honestly, now that I think about it, the graph we had originally also works So this is our original graph. As you guys can tell, the minimum number of nodes you need is this node and this node, right? But what can happen is if we don't pick this edge to start out with, let's say we pick this one, right? We pick this edge, then that's going to add 2 nodes already, this one and this one. And then we're going to remove all the adjacent edges. So we're going to remove this edge, we're going to remove this edge, we're going to remove this edge. Now what's going to happen is now we still need, we still have edges left that are not seen by these 2 nodes. So, maybe we pick this edge, which means our algorithm ends up adding this node and this node, right? And now we remove all the other edges, right? But now our all seen set is actually of size 4. So it was not the smallest, right? And that is the example that you can consider for why this algorithm doesn't work. Cool. Okay, moving on to the next question. Let's go to problem 2. Hopefully that explanation made sense to you guys. Plucky the Penguin has a cooler with capacity Q ounces. So we have a cooler with Q ounces. He goes over to the convenience store where there are N flavors of slushies. So we have N flavors of slushies. Each slushy flavor has a cost per ounce. So we have a VI, which is our cost per ounce of the ith slushie, and a quantity QI, which is how much we have, okay, of that slushie. For any real number, so for any number 0 to QI, so you can actually take any amount you want as long as it's not bigger than QI because you don't have more than QI. And we also know that the cost of taking that much slushy is X times VI. So if we take X amount of slushy I, if we take 5 ounces of slushy I, as long as there are 5 ounces to take, then the total cost is going to be the 5 ounces times the cost per ounce, right? Cool. Now that Plucky can take fractional amounts of each slushy, right? So he can take any amount he wants, any fraction, any percentage, right? For example, perhaps there's 36 ounces of a blue raspberry flavored slushy. He can take 12.345 ounces if he wants, right? So he wants to create the most expensive slushy concoction in the cooler, okay? So what that means is he wants to choose some amount xi greater than 0, greater than or equal to 0. So for each type of slushy, strawberry, chocolate, whatever, he wants to pick some amount for each one, okay? But his goal is to maximize the value of the cooler, which means for every amount that he picked, the total cost is going to be VI times XI, so how much ever that cost per ounce, times how much ever he picked to take, right? And if you add up all of that, you add them all up over all the possible slushies he could take, that's going to give you the total cost. Now, he does have a couple of restrictions, which is he cannot fit more than Q ounces into his cooler, right? So this is his capacity, right? And he cannot take more than what is available, right? So these are pretty reasonable restrictions, which xi is greater than or equal to 0, but it also cannot be more than qi, which is how much there is available, right? So what we're going to do is we're going to assume, first of all, this is an interesting assumption that you need to take into consideration, that there is always enough slushy to fill the cooler, okay? So if you add up all the slushy available, right, there will always be enough to fill up the cooler. Okay. So let's move on to question 2.1. Hopefully you guys understand the problem statement. So we have a cooler, fits Q ounces. We're trying to fill it in with slushies. Each slushy type has a different cost per ounce, which is going to be given by VI. And our job is to pick a bunch of XIs, which is like, this is how much we're going to take of the chocolate. This is how much we're going to take of the strawberry, right? Because we're going to take the most expensive ones, basically. Okay. And that's what 2.1 asks. So suppose Plucky has already, he's already filled in the cooler with some stuff. Okay. And there's some amount of each slushy left. So you have some amount, you have some slushy of all of them. slushy amount left for all of them. Okay. Which flavor should he pick next? Like, and how much? Like, which flavor and how much should he take off next? Right. And basically, this is going to be a greedy algorithm. So we're just looking here for a short answer. So I encourage you to pause and think about it. Like, which flavor would you take next, and how much of that flavor would you take? And basically, the answer here is take the most expensive slushy per ounce, right? So the one with the biggest VI, so the one that costs the most, take that one and take as much as you can. So this is two things. It fits in the cooler, and there's still left. There's still some left, and you take all of it, right? So the greedy, and that's the greedy algorithm, and this algorithm will work. It will give you, the most expensive. And why is that? That's because as opposed to the knapsack where we had objects that weighed a fixed amount of pounds, right? So sometimes, if you take, it'll like leave you empty space in your backpack. For this problem, because we're, taking slushies, and you can take an arbitrary amount of any slushie, right? The one that is the most valuable is always the most valuable, because you don't ever end up like having to take the most valuable one and then you have space left over. You can always fill that space with the second most valuable one. Right, so that's why the greedy algorithm actually works in this example. But we're going to walk through the proof of correctness. So if you didn't understand that, no worry, but this is for 2.1. And, moving on to 2.2, we say design a greedy algorithm that takes the input Q along with tuples. So again, we're going to have an algorithm, which is, it's just trying to maximize our stuff. Our input is going to be Q, which is the capacity, right? It is going to be, let me zoom out a little bit. It's going to be Q, which is our capacity. It's also going to be I, VI, QI, which is going to be basically a vector of tuples, which corresponds to, the ith slushy cost VI, per ounce, and there's QI ounces of it available. Okay, that makes sense. And what we want to do is we want to output. So our output here, and we're told this, is the tuples IXI. So we're going to output IXI such that, so basically we're going to say for the ith slushy, how much of it do we take, right? Such that the value of our cooler is as big as possible. Cool. And then we're also told our algorithm needs to be n log n. So I encourage you guys, and then we have running time. I encourage you to pause the video and try to think of an algorithm that takes n log n running time that solves this problem. So you start out with an empty cooler that has Q capacity, and it's a greedy algorithm. Hint, hint, look at what we talked about in 2.1, and then try to see if you can think of an answer to this. Cool, now that you're back, let's go ahead and write out the pseudocode for this. So the very, very first thing that we're gonna do is we are going to sort, sorry, this is I. We're going to sort I, VI, QI by the cost in decreasing order. So step one is, do this, sort by decreasing order, and we're going to say, sorted is going to equal to this. So we're going to sort I, VI, QI by VI in decreasing order. Okay, so maybe we say this by VI And instead of sorting it increasing, we say, decreasing equals true. So maybe that's what our pseudocode is going to look like for this. Let me make this a little bigger. Okay. Then we're just going to iterate over each of the elements in that order. So we're going to have I, Vi, Qi, and sorted, right? So now we're iterating over them in order. And what we're going to do is we're going to, like we said in 2.1, if we already have some stuff in the cooler and at the beginning it's going to start empty, let's take the most expensive one, as much of it as we can. So how much are we going to take? We're going to take the minimum of how much there is, Qi, and how much space we have left. So I'm going to say the space we have left is going to be Q here. And you'll see that we're going to actually update Q later to be minus, Q equals Q minus how much we took. Okay. And then, so that's how much we're going to take. So because we're going to take that much, again, our output, if you guys remember, so the output is these xi, vi. So we're going to say output is this list. And what we're going to do is we're going to do output push back, and we're going to put in I and how much ever we took. Okay. And you'll notice that what's going to happen is eventually this Q minus take, Q is going to become 0 because we're not going to have any space left. So we're going to keep iterating, but we're actually not going to take any of them. You can have an extra if statement to maybe exit a little early, but that's not a problem. And again, this is where we assume that we can fill up Q, right? That there's enough, and that's a fine assumption because the problem statement says like, hey, assume that you have enough slushy where you can always fill up Q. Okay. So once we're done with that for loop, we just return our output, and that is a pseudocode. The English explanation of what's going on, I just described it to you. And then now we can talk about the running time, and we would say, well, sorting takes n log n, right? Because there's n items here, and the fastest way we know to sort, assuming we know nothing else about the items, is n log n. And then this for loop, this is just going to be O of n, right? It's just we're just iterating over our elements. And then for each element, we're taking a minimum of 2 numbers. So taking the minimum of 2 numbers is O of 1. And then we're, pushing back into a vector. So that's O of 1. And then we are subtracting a number. So that's also O of 1. So the total running time is actually dominated by the sorting at the beginning, which is going to give you big O of n log n. Cool. All right. So let's move on to the next section. Hopefully you guys understood that part of the assignment. And now we're going to be talking about a proof of correctness. So actually, I give you the inductive hypothesis and the base case. So let's make sure we understand these. So again, for a proof of correctness, you need 3 things. You need 4 things. You need, mainly 3 things, but the 4th one is kind of free. You need a base case. You need an inductive hypothesis, which is the statement you're trying to prove. You need an inductive step, which is your argument for why the inductive hypothesis is true when you take one more step. And then you need a conclusion, which basically is just, at the end, our inductive hypothesis is true, which is actually equal to solving the original problem that we wanted. So for our base case here, we're going to say that any optimal solution that we are considering for this problem extends the empty solution, right? So the inductive hypothesis holds for t equals 0. And let's talk about the inductive hypothesis, right? So the inductive hypothesis that I give you is this one, which is after making the teeth greedy choice. So after we make the teeth choice, the greedy one, which we're choosing right here. So this is this is the greedy choice, which is we're choosing to take this much of a particular slushy, right? And we're saying the ith slushy, right? Sorted in this way. So after the teeth greedy choice, there is an optimal solution, right? That extends the solution the algorithm has constructed so far. So after we've made the teeth choice, there is still an optimal solution that includes all the choices we've made so far. That's what we're trying to prove, okay? And that's what I'm asking you for. So I actually want you to prove the inductive step. So this is what that looks like, right? So you start with assuming the inductive hypothesis holds for t minus 1. So what does that mean? That means that after t minus 1 steps, or after t minus 1 choices, so we've picked t minus 1 slushy types, okay? There is an optimal solution that extends, that extends the solution so far. Call that solution T, right? So that means that for the slushies, so for slushies from, let's say, like, again, in order, because the way we do it is after t minus 1 choices, right? So that means we've already taken the most expensive ones to the first t minus 1 most expensive ones, right? So call that T. T contains as much slushy possible. So T contains the most expensive T minus 1 slushies by cost per ounce, right? Because we built it, and we're assuming that there is still an optimal solution that has the first t minus 1 things that we've picked, okay? Right? So that means that our optimal solution T, let's call it T star. Usually you see this a lot. T star contains contains the most expensive t minus 1 slushies by cost per ounce, right? And there's two choices. And like it either contains all of them, all of them, how much ever was available, okay? Or the last one is partially contained, right? Okay, so either we've taken everything of the top t minus 1, right? Or there's a little bit left for the very last one that we actually took something off, right? Or I guess there's another option, or we've taken nothing. Okay. Now what we want to argue is after our next choice, so after we take the teeth choice that are greedy, after our next greedy choice, okay, there is still an optimal solution that extends our solution so far, right? So okay. So our algorithm is going to want to take some amount of the teeth item, okay? There's two cases. Either that amount is the same that T star indicates to take, right? In which case we are done because T star is still an optimal solution, okay? The other case, so case 2, is the amount we want to take is different from the amount that T star says we should take. So for the teeth slushy, T star has a different amount from what our greedy wants to take. Okay? But now what we consider is we say, well, T star has a different amount from what our greedy wants to take, right? For the teeth slushy. So our teeth slushy has two options. We either take enough to fill in, the rest of the container, or we take as much as there is, right? So we're always like taking the maximum basically possible, right? So that means that T star must be taking less of the teeth slushy than we are, right? But is still optimal, okay? So somehow it's taking less than, it can take at most as much of the T slushy, taking at most as much of the T slushy as we are, okay? Because we always take the most, right? And we've already done the T-1 choices, so there's only so much space left. And we always either take as much as there is left of the slushy itself, right? So as much as possible, or we take as much as fits, right? So that means T star, if it's taking a different amount, it has to take less than either, it has to take less than what is available of the T slushy, or less than it fits, right? So that means there is some other slushy that it is taking that has like a different cost, not a different, but there's some other slushy that is filling up the extra space in T star, okay? However, our teeth slushy is the most valuable per ounce, right? Therefore, the other slushy in T star cannot be better, cannot be more valuable, okay? And because of that, that means that we can actually swap some other slushy amount for the teeth slushy. So we can convert this T star into a solution that is what our greedy wants, and we still have the most valuable cooler. Okay. So case 2 is the more difficult one, but once you've gotten through case 1 and case 2, that gives you, this is the proof for the inductive step. And what's after the inductive step is you can actually just see that for the conclusion, right, you can just say after the nth greedy choice, right, there is an optimal solution that extends our solution to the algorithm so far. By the inductive hypothesis, there is an optimal solution that extends the solution that the algorithm has constructed so far, right? Therefore, but the only way to extend our solution is to do nothing to it, right? Because we've already picked all of the slushies. We've already processed all of these slushies. There's nothing we can do to extend it. We've hit the capacity for how much we can fit, right? We're at capacity. Therefore, our final solution is correct. Okay. Cool. So let's move on to problem 3. This is Monkey Island. So the way this works is one day you're stranded at a beach island with n monkeys. So you have n monkeys. Okay. You'll be there a while, but you want to make friends with all the monkeys. However, you don't want to leave the beach since the rest of the island looks dangerous. So each monkey I will only be on the beach during AI/BI. Okay. So for some amount of time, so this is AI/BI. So this is, like from 1 p.m. to 3 p.m., monkey I will be on the beach, okay? And you don't want to leave the beach. You don't want to go meet each monkey. But when they're on the beach, you can introduce yourself to monkey I, okay? So what you plan to do is you plan to stand at the middle of the beach, and you're going to use the megaphone that you brought with you to say hello at certain times, okay? Any monkey that's on the beach when you say hello is going to hear you say hello. It is okay if a monkey hears you more than once, that's fine. But you want to make sure that every monkey hears your introduction at least once, right? So goal, introduce yourself to every monkey without leaving the beach by using your microphone. Okay? So that's the problem statement. Hopefully you guys understand that. So monkeys are going to be on the beach only for one time period, right? From AI/BI. That's it. It's the only time period. And your goal is to introduce yourself to those monkeys that are on the beach during that time. Okay? So the battery in your microphone is low, so you want to minimize M. Okay? So you want to minimize right? So the goal is introduce yourself to every monkey without leaving the beach, right? By using your microphone. So obviously what you could do is you could just say like, well, when a new monkey, or just, when a monkey walks into the beach, I say hello, right? So that means you will say hello, n times, because there's n monkeys. And you could just say like, well, every time a new monkey comes on, I'll just say hello to him, right? However, what you want to do for 3.1 is it says you have low battery, so you want to minimize m. Want to minimize m, which is how many times you say hello. So you want to say hello the least number of times. For example, let's say you have a monkey that comes at 1 p.m. He's not going to leave till 10 p.m. Okay. Then, you've got several monkeys here, right? The next one comes at 2, then at 3, then at 4, then at 5, then at 6, right? If you say hello as soon as the first monkey comes, you'll only say hello to him. So, you'll be like, hello. Then when the next monkey comes, you'll be like, oh, hi, hello, you. Then when the next monkey comes, you'll be like, oh, hello, you. Then, hello, you, and so on. So you'll actually have to say hello. For this example, you have to say it 6 times, right? However, if you wait instead, right? If you wait till, say, 6 p.m. to say hello once, then because all of the monkeys are still on the beach at that time, by saying hello once, you say hello to everyone. Okay? So that's what we mean, like we want to minimize. There's many different ways to say hello, right? The most obvious way is you just say, like, as soon as a monkey comes on the beach, you say hello, right? But obviously that does not minimize, as this example shows, the number of times you say hello. It actually, I would say, maximizes the number of times you say hello, right? But we want to minimize it, okay? So the goal of 3.1 is I want you to come up with a greedy algorithm, right? So we're going to start our pseudocode. We're going to call it algorithm. And our input is going to be I, which is the intervals when the monkeys come to say hello to you. So, or when the monkeys come to the beach. So I is a list of AI, BI intervals as described, and your output is going to be a list T1 ... TM of times when you say hello, right? So for this example here, our output would just be the list that says, hey, I say hello at 6 p.m., or, I say hello at 7 p.m. or whatever, okay? I encourage you to pause the video and try to see if you can think of a greedy solution. You also want your running time to be O of n log n, okay? Cool. Okay, so hopefully you guys are back after you paused the video for a second and you thought of a possible greedy solution to this problem. So again, we're looking for a greedy solution, which means we don't really want to do that much work. We just want to decide to say hello, and then we're going to kind of forget about it and then just wait for the next time when we say hello. And, one way to really think about this is you kind of want to wait to say hello. Like if more monkeys are coming, right? So for example, for this example, you don't want to say hello at 2 p.m. because maybe more monkeys are going to come, right? So as the monkeys come to the beach, you wait and wait and wait until a monkey's about to leave, right? And as the monkey is leaving, right, then you can say hello because he's that is the last possible time you can say hello to that monkey. Therefore, if you don't say hello then, you will have missed the monkey, which is the thing you have to avoid, right? So in a sense, the greedy solution in this case is wait till the last possible minute to say hello and then say hello, right? Because what that means is that you are accumulating as many monkeys as possible on the beach. And then as soon as that one monkey is about to leave, then you say hello. So for example, if you had this 1 p.m., and let's say this guy's going to leave at 6 p.m., right? then what you would do is you would wait, or let's say he's going to leave at 5 p.m., right? You would wait until the 5 p.m. monkey gets here, and then because this guy's about to leave, then you would be like, oh, hello, right? And then all of these monkeys you would have said hello to, so you forget about them, you don't care about them anymore, and now you just wait, oh, then this monkey comes, and then he leaves at 10, right? So, at 5 p.m., you say hello, and then here you wait, and then at 10 p.m., right when he's gonna leave, you're like, oh, hello, right? And that's how you get this monkey, right? And that's actually, that would be the optimal because, if you wait any longer to say hello, this monkey's gonna leave, the one on line 20, so you'll miss him and you'll never get to say hello to him, right? So what you want to do then in that case is you want to sort your list of monkeys by the time they're going to leave, right? And essentially every time a monkey leaves, you want to say hello when a monkey that is not already on the beach leaves, right? So you want to process. So here's the idea. So we need to know when the next monkey we have not said hello to is going to leave, right? So one way to do this is we can sort our input by leave time and iterate over it, okay? So actually, do we want to do this? Because the monkey that leaves, so that means we would process it. Yes, we would process it this way. Yes, so we sort by leave time. So we know at 5 p.m. we're going to say hello, which then means any monkey that came before 5 p.m. we will skip in our sorting. So what this would look like is you would have, we're sorting by leave time. So you would have something like this, and you'd say, I'm going to leave at 5 p.m. So what we want to do is we want to sort by leave time, sort input by leave time first, and then by start time. So what that would look like is in this case, our input would get sorted like this. And then what we can do is we can iterate, we can keep track of the time when we last said hello. So this 5 p.m. And then as we iterate over everybody else, if you came before 5 p.m., then we don't count you, right? We basically skip you in a way because we don't care when you leave because we've already said hi to you, right? Because you already came before 5 p.m. But then eventually when we get to this guy, which is at 6 p.m., then we know that at 10 p.m., which is when he leaves, we will have to say goodbye. Because again, we are sorting first by leave time. So we'll always get the monkey that leaves first. And then we're just trying to find the monkey that leaves first, but that we have not yet said hello to. And the last time we said hello was 5 p.m. So when we get to this guy at 6 p.m., we know that we have to say hello at 10 p.m. And I guess actually it doesn't matter if you sort by the second one. We definitely need to sort by last time. So with that in mind, then what we would do is we would say, sort I by second element. Okay. So this is sort by leave time, right? And then we would say increasing. We sorted increasing. Okay. So that's sorted. And then we say for, AI, BI, and sorted. So we are iterating over the list that we just sorted. Let's say intervals. Let's call it intervals, right? Then the times, when we say hello, it's going to start empty. And what we're going to do is we're going to say last hello was, let's say, none. Or well, we have to say hello the very first time. So let's do something like this. So we know for sure we're going to say hello at intervals 0, 1. So whatever was the earliest time somebody left, we definitely said hello at that time because we had to say hello to that monkey before he left. And this is also, the last time we said hello. So now we iterate over the intervals, and then we say, okay, if the monkey arrived after we last said hello, right? Then, and now because we've sorted our intervals, he has arrived after we last said hello, and he is the next to leave, right? So he is going to be the next one to leave at some time bi. So more monkeys might still come, but he's going to be the next one that's going to leave because he's the one that leaves the next earliest. So we have to say hello to him at the time that he leaves. So we say times pushback bi, and then we said last hello was at bi. Okay. And then we keep iterating over this. So again, what you'll notice is that for all, for this monkey, what will be is we'll say hello at 5 p.m. So we'll get to this array and we'll say, well, 1 p.m. is actually before our last hello. So we already said hello to him. So, this guy's going to get skipped. This guy's going to get skipped. This guy's going to get skipped. This guy as well is going to get skipped. And it's only when we get to the 6 p.m. where we have AI is bigger than last hello that we're going to add 10 p.m. to our hello when we last said it, right? We're basically going to say, oh, I'm going to say hello at 10 p.m. when you leave, right? And so this guy does not get skipped. So we do say, so what we do is we add at 5 p.m. gets added here, and then at 10 p.m. gets added here. And then maybe, some people that are going to leave earlier. So let's say this guy was going to leave at, actually, no, but everybody that comes after has to leave after 10 p.m. So this guy was going to leave at 11 p.m., but let's say he got here at, 11 p.m. Let's say he got here at 10:30 p.m., right? Then because he gets here after we last said hello, we'll also add his thing, at 11 p.m., I'm going to say hello to you, right? That's one option. Another option is he actually got here before we last said hello, in which case we just skip him because he's going to get caught by like our at 10 p.m. say hello thing, right? So that's the greedy algorithm. And then at the very end, we return the times that we said hello. And this is the pseudocode. The English description, we just went over it. And you want to justify the running time. So again, the sorting alone is going to take n log n. And then this for loop is just O of n because we're just iterating over our elements. So the total running time is dominated by the sorting, so it's going to be n log n. Now the last part for 3.2 is we're expecting a proof of correctness. So we want you to give a formal proof that your algorithm is correct. So what I expect here is a proof by induction. So again, I want, I want a base case. You want an inductive hypothesis. You want a base case. You want the inductive step, and you want a conclusion. So there's 4 things that you want to discuss in that order. And basically, I'll give you a few of these. So I encourage you to pause to think for a little bit. But honestly, the inductive hypothesis for almost all the greedy algorithms are not that different. So if we go back to the previous problem, we have that our inductive hypothesis was this. And actually, our inductive hypothesis here is basically going to be the same, which is after making the teeth greedy choice. So after we have decided to say hello, or actually what you'll notice is that for every item we iterate over, sometimes we decide to say hello, and then there's also the else statement, which is like, don't say hello, right? So each of these is a decision, right? So either you decide to say hello or you decide not to say hello. So what we're saying is like after making the teeth greedy choice, which is basically just like, once we're in the teeth iteration, there's an optimal solution that extends the solution that the algorithm has constructed so far. Okay, So for the base case, this is actually exactly the same as the base case from the previous one as well, which is, hey, any optimal solution extends the empty solution because, you know, extending means you can add stuff to it to make it optimal. So like the empty solution can always be extended to be made optimal, right? Because it hasn't rolled out a solution. So obviously this holds, before we make any decision. So actually before this one, before even this, it's not just the for loop. Before we add our intervals, 0, 1, we have it is possible to have an optimal solution that has all the decisions we've made before, right? That's the base case. And now the inductive step is going to say, again, very similar to before, which is that inductive step, which is this, okay? We want to assume that our inductive hypothesis is true for t minus 1. So after the t minus 1 decision of whether to say hello or not say hello, we want to prove that there is still a solution that can be made from all of our decisions we have made plus our teeth decision. Okay, so we know there's a solution that we can make from all the first t minus 1 decisions of say hello, not say hello, right? What we want to show is that if that's true, there is some optimal solution, then it will also be true after we make our teeth decision, okay? And this is actually pretty straightforward again. So consider T star the optimal solution extending the first, T minus 1 decisions, right? Where we're like, oh, we either said hello or we didn't say hello at that particular time, right? And this is like the particular times are, sorted by time the monkeys leave, right? So for each time a monkey's going to leave, we either decide to say hello or we don't decide to say hello. We've processed the first t minus 1. We know there's an optimal solution that extends those. We're going to assume that, right? Like we know that's true. So we're going to call it t star. Okay. And now what we want to show is that when we make our teeth decision, there is still an optimal solution that extends all t decisions so far. Okay, so one option is, we either decide to do the ending time for that monkey, or we decide not to, right? So in either case, it might be that T star decides to do the same thing as greedy. That's case 1. Okay. In such a case, we're done. Because our T star that we had before for the first T minus 1 decisions also extends the first T decisions because it decides to do the same thing as greedy in the teeth decision, right? Case 2 is T star does the opposite or does something different for the teeth decision, right? So it's like T star is an optimal set of times when you say hello, right? And it's a minimal, right? It's going to be the minimum number of times that you say hello, right? And basically what's happening at the teeth time, so when the teeth monkey to leave is about to leave, right? So at that time, T star decides, like our algorithm will say hello. We'll say hello at the time that the teeth monkey leaves. Okay, what we're saying is, well, T star does not. Okay, so it did not say hello at the time that monkey left. Okay, so T star could not say hello after the monkey left because the monkey has already left, right? So it must have said hello to that monkey earlier, right? At some point earlier in time, it must have said hello to the monkey that just left, right? Now, because, we also know that it said hello to the first t minus 1 monkeys, and this matched our greedy solution, right? So by assumption. So that means that t star had to say hello to monkey t somewhere in between t minus 1 leaving, and t leaving, right? So it did not say it when t left, like at the very last possible time. It had to say it somewhere before, but it couldn't say it before t minus 1 left because the t minus 1 monkeys, all of those decisions were the same as our greedy decisions. So it had to say it somewhere between t minus 1 and t leaving, right? That's when it said hello to the monkey. And, or like, this is the worst possible case. Now, the argument is if we take that hello and say it right as monkey t leaves, we don't miss any monkeys. And that should be obvious because since no monkeys have left in between, then it actually doesn't matter when you say it, right? So saying it all the way to the end, which is what our greedy algorithm wants to do, is still correct, or like it's still an optimal solution. And that's basically it. We don't miss any monkeys, so it is still optimal. And then for the conclusion, again, it's basically the same thing here, which is after the nth greedy choice by the inductive hypothesis, there's an optimal solution, which is just a fancy way of saying that our algorithm is correct. Cool. All right, so that's for the written part. Let's go ahead and hop on over to the coding portion. So the coding portion is actually a little bit shorter than the others. And I'm going to see if I can actually, let's see, I'm going to see if I can log in to a different account so I can actually show you guys what this looks like. So instead of to my professor account, let me log into a separate Replit account. And let's go. Okay, let's go to Teams here. And right, okay, so we're starting, yeah. So this is homework 9 code. Oh, I don't want notifications. Okay, so this homework 9 code is pretty straightforward. It's actually just 2 problems. Both of them are greedy, so I'll let you guys know that. It is not out of 31 points. It is out of 30 points, so I need to fix that. Actually, it's not even out of 30 points, it's out of 25 points. I don't know why I have 31 there. It's out of 25 points. But yeah, so let's go ahead and jump right in. If you guys use any external sources to solve these problems, just add them to citations.txt, please. Otherwise, yeah, let's take a look. So the first one is called classroom scheduling. So you're a register at the school and you receive a schedule for N classes. Okay, so hopefully you guys can see, can read this pretty well in the video, but let's take a look at that. So you receive you register for school and you receive a schedule for N classes. So you have N classes you need to schedule, okay? You wanna fit all N classes into as few classrooms as possible. So goal, use as few classrooms as possible for all N classes. And you want the minimum number of classrooms. So what's going to go here is like, here's the restrictions. 2 classes cannot happen in the same classroom at the same time. So, you're given when a class starts and when it ends. And 2 classes cannot start and end, cannot overlap with each other and be in the same classroom. Okay. Now, all classes in all classrooms are of the same size, so we don't need to worry about capacity. So we don't have like certain classrooms are smaller or bigger. They're like every classroom can fit any class. Okay. Now, the other thing is that the time that we're given, it does include a buffer, right? So you don't have, so for example, I think I'll walk through the examples that we have here, but you can have a class that ends at 10 and a class that starts at 10, and they can use the same classroom because they start and end at the same time. So you can assume that like there's already like if I give you, oh, this class is from 12 to 1, and then another class is from 1 to 2, you actually only need one classroom because as soon as the first class ends, the next class can take over. And then the goal is to implement this function called find classrooms needed here in answers.cpp, so right here, that returns the minimum number of classrooms you need to fit the n classes. The n classes are going to be given as the start and ending time, so it's going to be a pair of numbers, two numbers, start and end, in a vector. Okay, and then for full credit, your algorithm needs to run an n log n time. Okay, so what I say is I do also give you a few hints. It says it may be helpful to construct a new vector that is also a vector of pairs, but instead of start ending times, it is time and then is start as a Boolean, like whether a new class started or whether it is an ending time or similar. And then you can use, I also say you can use standard sort from the algorithm header, and you may find this resource helpful. So I encourage you to sorting vector of pairs in C++. So we're going to do this together, but let's walk through a few examples to make sure everybody understands what's going on. So for example, for this first class, we have the classes 0, 4, 4, 8, 2, 10, and 6, 10. So what this says is, this class starts at time 0 and ends at time 4. This one starts at time 4, ends at time 8. This one starts at time 2, ends at time 10. And this starts at time 6 and ends at time 10, right? So we need at minimum 3 classrooms. Why? Because you need one classroom for this one, 0, 4, right? Then you need, this could be in the same classroom as the first one. So 4, 8 can actually be in the same classroom as 0, 4. That's fine because they don't overlap. But this 2 to 10 overlaps the 4, 8, so it needs a different classroom. And similarly, this 6 to 10 overlaps with the 2, 10, and it overlaps with the 4, 8. So it needs, a separate classroom. And another way to see that is that classes 1, classes 2, classes 3, they all overlap from 4 to 8. So from 4 to 8, all 3 classes are in session, which means you need at minimum 3 classrooms. Similarly, for classes 2 here, you actually only need one classroom because there is no overlap. So again, like I said, this one goes from 1 to 5. This one goes from 5 to 10. You can immediately switch. And this goes from 10 to 17, which means you can immediately switch. And then for the last example, if there's no classes, then you need no classrooms, right? So I encourage you to pause the video and give the algorithm a try. Again, it's greedy, so something reasonable that you think of might help. And again, I do encourage you to look at this hint, which is like, maybe you want to think about like time and is start. Instead of start end times, you might consider like, how can I transform that into something where like I can keep count of how many classrooms I need, because this is how many classes have started. How many, essentially, hopefully you've thought about this a little bit, but what you want to know essentially is you want to know how many classes are running concurrently, right? Because if there's ever a set of classes that are running, at the same time, then you need separate classrooms for them. So if you can find what is the maximum number of classes that run concurrently, then you will be able to identify what is the minimum number of classrooms that you need. Cool. All right, so with that in mind, so that's the idea, which is like figure out the number of classes that run concurrently. Following the hint, the very first thing we're going to do is we're going to transform our input into time and then is start. Okay, so we're going to iterate over, we are going to iterate over our input. So for, let's say class, let's call it course in classes, we are going to have a timeline that's going to start out as empty. It's going to be, like the hint suggests, a vector of pairs of ints and booleans. Okay. And what we'll do is we'll say, well, timeline dot push back. For this one class, we know that we have course dot first is going to be the start time. So this is going to be the start time. So we're going to set it to true. And we're also going to add a course dot second is going to be the end time, and we're going to set this to false. So this is based on the hint. And the reason I want to do this will come obvious in a second, which is now I am going to sort the timeline so that it is chronologically in order. Right? So we can actually use standard sort here, and we can pass it timeline.begin and timeline.end to sort them. And you'll actually notice, so if you read this, if you read this stuff here, it does turn out that when you call standard sort, you can also tell it how to sort. Yeah, so vec_begin.end. By default, it is going to sort by the first element in your tuple. So by default, this sorts using the first element in the tuple in increasing order, and then the second element. Okay? So for our example here, for example, this classes, this is what we started with, 0444. Once we're done with the for loop, our timeline is actually going to look like this. It's going to look like 0, true, 4, false, 4, true, 8, false, 2, true, 10, false, 6, true, 10, false. Okay, so this is what our timeline looks like, because we, for each of these elements, we created 2 tuples, one which is true, one which is false. Okay, and then after we sort it, this is going to first get sorted by the 0, right? So by the first element. So we're actually going to have, this same vector of elements here, but now it's going to be sorted where 0 comes first, then 4, actually then this 2, right? Then what it'll do is it'll actually sort. So we have 2 4s, so they should come next. However, it will first sort then it'll sort by the second element. So it'll actually, it'll have this false come first because it'll sort by the second element. And false is 0 in C++, so it comes before true. Okay, so both of the 4s will come next. Then we'll have the 6 come here, then the 8, then both of the 10s, where the false one comes first. Actually, they're both false, so it doesn't matter. They're actually exactly the same, so it doesn't matter what order they come in. Okay. And now you'll notice that because now it's sorted, one way to figure out how many classes are running concurrently is we can just say, well, at time 0, we had a class start. So we have 1 class running. At time 2, we had another class start. So we have 2 classes running, right? Now at time 4, some class ended. So actually now we only have 1 class running. But at time 4, another class started. So we went from 0, so if we walk this in order, we went from 0 to 1 to 2. We started with no classes running. Then we went to 1 by looking at this first one because 1 class started. Then 2. Then we went back down to 1 because 1 class ended. Then we went back up to 2 because a class also started. Then we went to 3 because another class started. Then we went down to 2, down to 1, down to 0. 1, down to 0. So that probably gives you a hint of like, hey, actually, now that we've sorted everything, we can very easily just figure out how many classes we had. So we can say, num classrooms starts at 0, and then we can say, for, let's iterate over our timeline, all right? If timeline.second, so if we are starting, if it.second, if we are starting a new class, then we need a new classroom because we know that we're starting it concurrently. Otherwise, we're ending a class, so we can free up a classroom, right? So we -1, and then at the end, we just return. So this num classrooms is keeping track of how many classes are running concurrently. And like we mentioned, our goal is to figure out what is the maximum, max classrooms used. So every time we change the variable, we can say, the max classrooms is just the maximum of whatever we had before and whatever, how many ever classrooms we are currently using concurrently. Cool. And that actually means that at the end, you can just return the maximum number of classrooms you ever saw that were used concurrently, because that's the minimum number of classrooms you need in order to fit the entire schedule. So that's for this part of the problem. Then we can jump into question 1. So this is a treasure cave. So again, let's make sure that everybody understands how they work. I do also want to explain this piece of code here. So we have a struct called metabar that has 2 values in it. It has a count and a value. And I also provide a less than operator. So what this means is that when you sort, it is actually going to use this operator to see which element is smaller than the other. So by this definition, you sort first by value. So whatever is in the value, the smaller value is going to be a smaller bar, no matter the count. And then if the values are the same, then a smaller count is going to be smaller, right? So we'll see this in an example, but first let's make sure we understand the problem. So you have a hidden cave filled with n different types of metal. Each type of metal bar has some value, and there are xi bars in the cave, okay? You want to bring back as many bars of treasure as you can, but your bag can only fit w bars, okay? How do you choose how many bars of each metal to bring home to maximize the total value, okay? So again, the difference here between knapsack and what we're doing now is that in this case, each bar weighs the same, right? So you can bring, you can bring at most W bars, but each bar weighs the same. So you're not worried about like accidentally taking the most valuable bar and then that preventing you from taking some, 2 bars that would have actually been more valuable together, right? Because every bar here actually weighs exactly the same. So what you would do is greedily, you would just take the bar that is the most valuable and you would take as much of it as you can, right? So that is the idea here for this algorithm again, right? So greedily take the most valuable bar and take as much of it as you can, right? And we can walk through a few examples here. So find best value, right? If you have no bars, then it's 0 because you have no bars. If you only have one, so here we have 2 bars, I think. Yeah, we have 2 bars. We have 4 of the first type, whose value is 1. So the total value you can take is actually 4 because we take 4 of the only bar that we have, right? Here we actually have 4 of the first type, 10 of the second type, 2 of the third type, 4 of the last type. And then the first type is worth 3, second type is worth 1, third type is worth 5, and the last type is worth $2 per bar. So what you would do is you would just take, as much of the most expensive bar. So you would take 2 of the third bar because it's worth $5 each. So you take as many as you can. There's only 2 of them, but you take all, they're worth 5 each. So that gives you $10 worth of value. Then you take the next most expensive bar, which is actually the very first bar, and there's 4 of them. So you can only take, you take all 4. And then the very last bar is the next most expensive. There's 4 of them, but you only have space to take 1 more. So you take one of the last bar worth 2. That gives you 24. And then you guys can look through the next examples. And again, the hint is you can use standard sort here, and the writing time should be n log n. So hopefully this is pretty straightforward for you guys. I encourage you to pause and to give it a shot yourself. But essentially, the very first thing that we're going to do is we're going to convert the counts and values into a vector of bars. So we're going to have our standard vector of metal bar, which is going to be our bars. And we are going to iterate over the size of our counts. Something like this. Oops. Sorry for that. And we're just going to say, bars dot push back. And the very first thing we have is a count and a value. So we're going to push back the counts I, and we're going to push back the values I. That is going to give us a vector of bars. So what does bars look like? So bars now looks like, let's take, it's a good, I think this first example is pretty good. So let's take this first example. This is what we started with here. W7 counts this, counts that. So after we iterate over this loop, we're actually going to have, 4, 3, because the count goes first, and then the value. We're going to have 4, 3, 10, 1, 2, 5, and 4, 2. Okay. So that's what we've done here. And then what we want to do is we want to sort these by value in decreasing order. So the difference here is we do actually want to do it in decreasing order. So it might be helpful for you to search standard.reverse. It's another useful function. I believe standard sort also might support sorting in decreasing order. I'm not sure, but you can always reverse after you sort. So we would first sort, our bars dot begin, bars dot end, so that, oops, I keep switching tabs. So that sorts our values, and then we can reverse them. So bars dot begin, bars dot end. So now we have, so after we sort it, so this is what it looks like after the for loop. After we sort it, so when we get here, it'll look like, the bar standard sort is going to use this comparator to compare the values. So it's actually going to sort by the value and then by the count. So this will be, the cheapest, the least valuable one is actually the 10, 1. So he'll be first. Okay. Then we'll have the 2, 5. No, the 4, 2. The next most valuable. Then we'll have the 4, 3. And finally the 2, 5. Okay. And then afterwards we reverse them. So, it's just flipping this backwards. So we're going to have 2, 5, 4, 3, 4, 2, and 10, 1 as the least. So now it's going from most valuable, which is $5, to the least valuable. And now that we have them sorted in reverse, we can just iterate through them, right? So we would have, we're iterating through each bar for the bars, but now, bars has been reversed. So we're iterating over them backwards. And we're, the first bar we're going to see is actually going to be this 5, which is the most valuable. So what we want to do is we want to take as much of it as we can. So we're going to say, how much we're going to take. We're going to take the minimum of, and you probably want to, it's algorithm's already there. Great. We are going to take the minimum of how much ever we can fit, how much more we can fit, and bar.count, which is how many there are. And then what we're going to do at the end, we're going to have, W minus equals how many we took. So from W, we're going to subtract that many. And what we want to do is we want to find the best value. So, value starts at 0, and we would say value plus equals. We took this many, and each one is worth this much value. So we took this many, it was worth this much value, so we add that to our total value, and then at the end, we return the value. And hopefully you guys were able to get through most of that on your own. These problems are, I hope, a lot easier than the previous ones you did. But you should be able to compile and then check to make sure 3, 1, 0, 0, 4, 24, 25, 35. If you jump over to the README, you will see that at least for these test cases, it is indeed 3, 1, 0, and then 0, 4, 24, 25, 35 for the answers that we have. So that's it for the walkthrough. Hope you guys enjoyed it, and I'll see you guys in class on Wednesday.